In the previous example, I indicated that all you gotta have are two conductors near each other and you have a capacitor. So the problem is, in most cases, calculating the capacitance is very, very difficult unless there's symmetry. So we had the parallel plate capacitor, and we have constant electric field in here. That makes it really easy to calculate. And then we had the cylindrical capacitor. Well, obviously we had cylindrical symmetry, so that's easy to calculate. There's one other pretty easy one to calculate, and that is a spherical capacitor. So imagine we have a sphere of radius R1, and we have another sphere here, and this outer sphere is radius R2. Okay, we put some charge on one, you put charge on the other. And so now we have an electric field. Okay, so now we're going to have a capacitance again. So same thing. We got a capacitance right here. And so we want to find, well, what is the capacitance? Well, capacitance is going to be Q over V. Okay, and so we got a Q on one, we got Q on the other, we got Q. So what's V? Well, the voltage is the voltage difference between the two. Okay, so the voltage difference between the two is going to be the voltage there and there. So we know that the voltage difference, the voltage on the inner one is going to be KQ over R, okay, and the voltage on R1 and the voltage on the outer one is going to be KQ over R2. Okay, so the difference in voltage, so the difference in voltage, because that's what this is difference in voltage, is going to be KQ 1 over R1 minus 1 over R2. Okay. So that's it. Okay. And so we can make that a little bit neater here. So the difference in voltage is KQ R2 minus R1 over R1 R2. Okay. Now, we plug that in over here, and say that the capacitance is going to be Q divided by KQ of R2 minus R1 over R1 R2. Okay. K, we know, is 1 over 4 pi epsilon naught Q R2 minus R1 over R1 R2. So the Q's cancel, and so the capacitance comes out to be 4 pi epsilon naught R1 R2 divided by R2 minus R1. Okay, and so there we have it. There we have the capacitance of a spherical capacitor. So that would be a sphere inside of a sphere. And so all you need to know is the R1 and the R2, and the rest of that is just the geometry, the 4 pi epsilon naught. Okay, and so again, notice what normally happens when we get to calculating capacitance is it all comes down, there's going to be an epsilon naught in there, and then the rest of this comes down to the geometry of how we have things laid out. Okay, now your book brings up an interesting sort of thing, and that is special case of we have a charge here, some Q on a sphere, and we have the outer sphere. What happens if we take the limit as R2 goes to infinity? In other words, what we have is just a charged sphere. Would that have capacitance? Would just a sphere of charge have capacitance? Well, yeah, because if you get something near it, then that charge can come off of there and release energy. And so, yeah, it's going to have just capacitance all by itself. So what would be the capacitance there? Well, again, we take the limit as R2 goes to infinity of the capacitance of a spherical capacitor. Okay, so that's going to be limit of R2 goes to infinity of 4 pi epsilon naught R1 R2 divided by R2 minus R1. Okay. Well, you take the limit as R2 goes to infinity. Okay, so L'Hopital's rule, take the derivative with respect to R2 at the top, the derivative with respect to R2 at the bottom, and what we come up with is 4 pi epsilon naught R1. So if we just have an isolated sphere of radius R right there, and we put some charge on it, okay, it doesn't matter positive or negative charge, we just put charge on it, okay, so we put charge on it, then what happens is the capacitance of that isolated sphere is simply going to be 4 pi epsilon naught R.